Okay, great. So this portion of the workshop is a tutorial on the steps that are necessary to fine-tune a particular neural network model and to eventually then run it on a robot wrapped in a ROS node. So the target audience for this is any new robotics team who are just setting up their robot or setting up some functionality on their robot. And so for me, at least, when I started working with robots, it was not obvious to me how to run something which worked well on data sets to then move this onto the robot to have it running in real time. And so I assume you already have some knowledge of deep learning and some knowledge of ROS. So that yeah, this is mainly then how to write a ROS node, which uses a deep learning model to perform some functionality. And yeah, in principle, this can apply to most type of models, but today we are specifically looking at using an activity recognition model for recognizing activities from videos. Yeah, so I will now share my screen. Okay. Yeah, so we actually start with an i3D model, which has been trained on the charades dataset, which is a daily activity recognition dataset. So this is the repository that we start with. And so obviously you are free to select any model that you already have. But ideally you want to start with something that already has the weights available from pre-training on some larger data set. And yeah, as we've seen in the previous presentation by Rafael, there are obviously better models for recognizing activities and gestures. But yeah, here we just use this i3D model as an example. So in the case of this model, they have some pre-trained weights for 4 different types of models. 2 of them are on actually trained on the charades dataset, and one uses optical flow as an input, and one uses this RGB or sequence of RGB images as an input. So we would actually use this one. So I have already cloned this repository onto laptop. Yeah, so if we look here at the so what we first want to do is now use this model to fine tune on our own data set, right? And if we look at the code that actually loads the data set, which is here, this is meant for loading images from the charades data set, and actually it expects the data set to be in the form of JPG files, whereas the data set that we have available in the metrics project is in the form of videos. So this is just yeah, it's a sequence of videos where we have all the videos in one folder and the labels in a text file which tell us the name of the video and the class ID. And this class ID is then also related to the list of activities here. So class 21 would be writing, for example. So what we need to do first is to replace this charades dataset loader with our own video dataset loader. So yeah, in the interest of time, I've already done this, but we will go through this to see what is actually going on in this video dataset. So in this helper function, it's actually going through all of the video files in a given folder, also opening the labels file, and in the end producing a dictionary which has a an array for each of the videos that are present in the video dataset. So if you want to actually explore what this dataset loader looks like, there's also a main function here where you can run. Maybe we'll run this right now. So this creates a dataset from this folder and with these labels. And if you then index an item from this dataset, you get the an actual clip, the label for that clip, and the ID of the video. So also we've defined what a clip consists of. In this case, it's a clip which consists of 20 frames. So yeah, given an index, it will get the current frame and up to 20 frames from the same video, which then consists of a clip. You'll also notice that it converts this actual each of the frames into a certain format, which is expected by the model that we are going to fine tune. Okay, so this is this video data set folder. So if we just run this, it will print, this is the size of the clip that it returns, and this is the label. So it's a one-hot encoded label, so it's a video which is belonging to the last class, which is actually what we saw in the labels. So the first video is of class 21, which is the last class in this. Okay, so apart from the dataset loading, the second thing we have to look at is the training loop. So in the original repository, they did have a training loop, but yeah, so to make it a bit more convenient, we use the PyTorch. Open it here. We use the PyTorch Lightning module to yeah, this just makes it more convenient to write the different parts of the training loop, and then internally the Lightning module takes care of actually running the training loop, right? So this is again something that you don't have to do. This is just yeah, written for convenience. So in this Lightning module, the functions we have to define are what happens when you pass an input through the network, so the forward pass, what happens during a single training step, and what are the optimizer, what is the optimizer to use, and what is the data loader to use. So in the data loader, we are just creating an object of this video data set, which we saw earlier, and we also apply transformations to the frames. And in this case, we are randomly cropping an image of this size, randomly horizontal, applying a horizontal flip randomly, and then eventually resizing it to 224. So this transform is also passed into the data set. And for the actual model that's used, so we are using this Inception i3D model, which is defined in the repository. So if you look at this PyTorch i3D file, this is where they define this Inception i3D model. And so this is just directly using the model that's provided by the authors of the repository. And if we are using the pre-trained weights from the charades dataset, then it the only thing it does is loads the weights here and also changes the number of outputs in the last layer, since in the charades dataset there are 157 classes from the original 400. And since in our case we have only, in this particular case, the activity recognition data set has 22 classes, we again replace the last layer with the number of classes that we have, which is 22. So then for the actual fine-tuning step, we we do, yeah, we want to freeze all of the layers except for the last layer, which has the, which outputs then the probabilities for each of the classes. So this step freezes all of the layers, and this step then unfreezes the last layer. So actually, this is the only layer that will be trained during our fine-tuning step. Yeah, so most of these steps are already available in the original training file. So we are yeah, using a binary cross entropy with logits for calculating the loss. Yeah, and everything else essentially remains the same. So they're using also using the stochastic gradient descent as the optimizer, which is the same as this. So in the end, this yeah, the PyTorch Lightning module is just a more convenient way to write the trainer. Yeah. In addition to this, then there's the main file, which was also added to create the Lightning trainer. So this is our trainer, and also additional arguments that we want to provide during training. And the actual arguments are then specified in the run script. So at the moment, we only have a training data set, which is actually what we call the validation set. So we are using that to fine-tune this model. These are the labels that we use, and we start from the RGB based charades dataset models weights. We have 22 classes, and in this case we use batch size of 8. Now, quite a high learning rate because we are only training the last layer. And if you have paused the training at some point and you want to resume from a previous checkpoint, then you can also include this argument. So that's yeah, that's basically it. So there were just the three files that we added, which were the video dataset file for loading our custom dataset, the PyTorch Lightning module class, which yeah, makes it simpler to use the training loop, and this main file, which then actually creates an object of this trainer. So since we have this ready, now it's actually ready to run. So we just run the run script, then it should start training. So I will just make sure that it starts and then kill it, because I'm not going to train the whole model here. So once it completes training, then you should see that there are some logs created, and you will eventually have saved checkpoints in this folder, which is what you will then use on your robot as a trained model. Yeah, so I just want to mention that we will also push this code onto the HeartMatch GitHub organization. So you'll find it here. So on github.com/HeartMatch, we will eventually push this a fork of this repository here with the additional code for fine-tuning on the metrics dataset. Okay. So now at this point, we assume that we have a trained model for our dataset, and we want to now run this on the robot. Yeah, so this means we need to, or in most cases, if your robot is running ROS, then you need to create a ROS node, which then loads this trained model and connects the images from the camera of the robot to this model, right? And so the main thing that we need to do in the ROS node is to save a sequence of images. So as we saw earlier, the clip size was 20, so we need to save up to 20 images from the robot's camera and convert it into the format that is expected by this i3D model. And finally, publish this the output of the model on some topic, which is the recognized activity. And yeah, so in our case, we will actually publish the top 5 most probable activities, so not just the most probable activity, right? And so before writing the ROS node, it's a good idea to use your robot to record a few bag files in which you record, the bag file consists of the camera images of the robot while someone is doing some type of activity in front of the robot. So this is your test data to run locally to test your ROS node. And if it works with the ROS bag file, then once you run the code on the robot, it should then run with the live system. Yeah, we should also keep in mind that you want to start and stop the node. So you may not want to run this activity recognition continuously on the robot. So the ROS node also needs some way to tell it to start and to stop. But obviously this is application dependent. So in your case, you might want to have it continuously running as well. So in that case, then there's no need to start and stop. And yeah, the other thing to keep in mind is that although we say that the model expects 20 frames as an input, this doesn't necessarily mean that an activity will be completed within the 20 frames. And so we want some way in this ROS node to accumulate results from multiple clips, and after a reasonable amount of time, then report what the detected activity is, right? So if it's 20 frames, that's probably not even a second. So it's probably 2/3 of a second. So you might want to accumulate clips up to, let's say, 60 seconds, which is at least 2 seconds or 3 seconds. So this is again dependent on your robot and the type of activities that you're detecting. So this is something you might have to play around with. Okay, so now we can look at the ROS node, which again is, so it's already written, so we're not going to develop it here, but we will go through the main parts of the code, and eventually the code will be, again, pushed to this HeartMet GitHub page. Yeah. So let's see. So from the original PyTorch i3D repository where we were training the model, there are only 3 files that are necessary. The first, actually, I'm not sure if the video dataset file is necessary at all, but the actual PyTorch i3D, which contains the definition of the Inception i3D model, that's definitely needed, and the i3D trainer. The PyTorch Lightning module is also needed, since we use this to load the checkpoint. So apart from those, we also have the trained checkpoint, which contains the weights of the model fine-tuned on our dataset, and the activities as well. So now looking at the actual node, which is a single file. Go here. So the main things to look at are, it's loading several parameters, which we define in the launch file. So this is where you would now customize it to your own robot. So you need to specify which is the topic from the camera of the robot, and where to publish the result. So in this case, we are publishing a result in the format that's expected by the metrics referee box, which I will show you in a second. It's the paths to the labels of the activities, and then this is the paths to the model that you'll actually use for recognizing the activities. using GPU. Clip length is 20 frames. And we also have two parameters which define how many clips are used to generate an intermediate result, in this case 10, and the final result is then using 50 clips, right? So actually, this is 50 clips with a moving windows, and the window is moved forward by 1 frame each. So actually, if you consider that there are 20 frames in a clip and we're getting 50 clips, it's in the end a total of roughly 70 frames that are actually used to decide the final result. So coming back to the node, so we load several parameters, and this is the part where we actually load the trained model. So using this i3D trainer object, we can load the checkpoint that was specified in the launch file. Yeah. And we also need to do the transformations into the size that we trained the model with. So in this case, 224, but we don't do any random cropping or flipping, right? So just center crop it and resize to the size that we expect. Okay. And yeah, then we define topics where we are publishing the result, the debug image, and the actual final result. And as I mentioned earlier, we also have a topic which decides when to start and stop the node. In this case, again, this is a command that is received from the metrics referee box, but you can obviously replace this with any other type of topic which defines how when your node should start and stop. So this is the callback. This is the callback for the image from the robot's camera. And here we are just converting the ROS message into an OpenCV message and storing it in a queue. And we only ever store images. The number of images would be equal to the clip size. So we store up to 20 frames and then get rid of the oldest frame as soon as we exceed this length. Some of this is not important. The main thing is that when the node has initialized, then it's just constantly waiting for a start command, and it's only once it receives the start command that it creates a subscriber for the image from the camera. So this is usually good practice because otherwise, as soon as you run the node, it's unnecessarily subscribed to the camera. Whereas what you want is that it only listens to the camera once you tell it that you want to recognize activities. Right? So once it receives the start command, then it goes into the running state, which is here. And yeah, so this is now implementing what I mentioned earlier, that we wait until we have at least 20 frames. And now this function, the get torch clip, is converting this sequence of frames into the format that is expected by the i3D model. And the recognize function is then taking this clip and actually passing it through the model to get the result. Right? So now we will just look at these two functions quickly. The get torch clip takes the input frames, converts it into the format that is required by the i3D model, also applies the transformation, so it crops it into the 224 by 224 and returns the clip. And the recognized clip itself is then, this is the line where it then passes it through the i3D model, gets the logits and also the overall prediction. So actually this, I think the prediction is not used at all, but it's mostly the logits that I use. So this is, in the end, the output of a softmax for each of the classes. And this is accumulated. And as I said, we want to accumulate this over several clips rather than taking the result of one clip. Yeah, so this is, and then this is the part of the code that actually publishes intermediate results and also the final result, right? So the intermediate results, at least for our case, is mostly for debugging, and also if you want to get continuous predictions over time, whereas this final result is only published once we have all 50 clips. So I think that's essentially it. The only other thing that's of importance here is that we are not just taking the class with the highest softmax score, but rather the top 5. Since we want to have the top 5 activity classes. And this then publishes an activity class, also creates an image with the activity classes as text. Yeah, that's basically it. So now we will actually try running this code. So yeah, but maybe before running this, so these are some bag files that were recorded on our robot. And if you, let's say, look at one of these, there were several topics recorded, but the topic that we're interested in is this image from the head camera of the robot. So that's what we will end up playing. Okay, so let's start. This is our score. And this is we now launch the ROS node, which is loading our trained model. Okay, it's ready to start. We have an image viewer for looking at the debug image. So this is, if you look at the list of topics, actually, we'll see that recognize activity debug image is is an image where we also show the activities. And that's essentially it. The command that we need to send to start this is then a metrics reflog messages command, where we need to specify the activity, which is so the task, which is activity recognition, and the command itself, which is start, which is what we'll publish here. So it just received the command to start the activity recognition. So now, as soon as it receives images on this camera topic, it will then start publishing the results. So we also will make here echo the final result from the node. Now we're ready to start playing bag file. So I mean, obviously, if this was the robot, then it would already have received the images from the camera and published the results. But since we are testing locally, we now need to play the bag file where we select the topic which we want to publish. This is the right one. Yeah. Okay, so at this point we can see that it's publishing these debug images with the top 5 classes, and it's completed. So it also published the final result, which so it has putting on taking off shoes as the top result and a few other ones which it also thinks are likely. And now you can repeat this several times. So we can tell it to start for task 3 in command 1. Started, and now we play a different bag file, so it's a different activity. doing this. This time it's someone walking into the door and closing it. Yeah, so again we get in this case the correct one and a few others which it also thinks are likely, and maybe a final one. So we need to first send the start command and play the back file. So this time it's someone who's taking something out of the fridge, and it looks like, yeah, several of these classes are incorrect. There is the last or the fifth most probable one is putting in, taking something out of the fridge. And also looking at the final result, yeah, it's the same case. So you have several incorrect detected activities, and the fifth most likely one is the one that we are targeting. And that is basically it. So at this point, then you're ready to then move this node onto your robot and run it with the live system. So that's it for this tutorial. So we will push the code for both of these, both the fine-tuning of the model and the actual ROS node which uses the fine-tuned model onto the GitHub page. And if you have any questions, you can ask them now, or create an issue on the GitHub repository and ask questions there.